Thank you, Sylvester, for the introduction. Today we'll be speaking about body-machine interfaces for advanced human-robot interaction. I will start with the description of the state of the art. So the operation of robotic system is still needed in a set of applications where human perception and decision-making skills are not yet able to be replaced by artificial intelligence. And some examples include underwater and space exploration, disaster scenarios, or minimally invasive surgery. Now, using the body instead of standard interfaces to control robots can result in an easier, faster, more intuitive, and more engaging teleoperation experience. And this is the motivation behind our studies. The main challenge when designing human-robot interfaces based on body motion, also called body-machine interfaces, is to find out a mapping between body motion and robot commands. And this mapping consists in a subset of the body parts that you want to track from the human body to control the robot, and how to translate motion into robot commands. Now, this challenge is smaller if you're controlling humanoid robots, because you can one-to-one map the motion of the person into the motion of the robot. But if you're controlling robots which are more complicated or very different from the human body, such as drones or mobile robots, that is a more challenging aspect. There are no standard ways of defining HRI mapping methods, but we can cluster them into two big families. So the first one is called data-independent mapping functions, and they're normally based on two main methods. So the first one is to find out a morphological correspondence between the human and the robot, and this works well with humanoid robots, for instance. Or mappings are defined in a heuristic way, leveraging, for instance, common human gestures that we use for human-to-human communication, such as go up, go down, take off, go right and left, these kind of gestures. They are data independent because they don't rely on the observation of how humans spontaneously interact with certain machines. The other cluster of methods is the data-driven methods. And one examples we probably all know in NCCR is the flight jacket. So what we did is, well, what they did before we arrived, is to observe how a set of people would move their body to control the flight of a drone. And based on the common interaction gestures and strategies, they derived this mapping functions, which was basically mapping the motion of the torso into roll and pitch commands for the robot. Now, this is a called general kind of approach because it relies on data from a set of people, and then we have one fixed interface that everybody will use after that based on the most common interaction patterns. The problem with this is that many people, well, actually everyone moves in a slightly different way, and we all have different tastes in terms of how we want to interact with robots. So some people might want to use their hands, some people might want to use their body in a different way. And that is why my scientific focus is on personalized motion mapping functions. So what I did in the last years during my PhD is to design machine learning algorithms to match human motion and let people use robots in a personalized way, so based on their spontaneous interaction strategies. So my presentation today is focused on three main points, which are part, as Sylvester said, are going to be part of my private defense next week. The first one is the personalization of body-machine interfaces, how it looks like, how it works, what are the results. Then we go into body-machine interface generation to control different robots, morphologically different robots. And then I will speak about the online adaptation of body-machine interface, so interfaces that change over time. About personalization of body-machine interfaces, the first thing we do is to try to extract the spontaneous body motion, interactions that people show to control a certain robot. Now, in this case, we were working on a fixed-wing drone, and we asked a set of people to move their body as if they were controlling the flight of a drone that they saw into a simulator. So we show them in first-person view on a head-mounted display the flight of a drone, and we asked them to move as if they were controlling it. And based on that, we extract the most important features. And then we run a regression algorithm, both linear and nonlinear, to see if there are differences. And everybody was then allowed to control the drone using the personalized mapping. So this is how it looks like. This is what we call imitation task. So the red line is the projection of the drone trajectory over time. And you see that this person is imitating the drone using their torso. So in this case, we see that this subject wants to use torso motion to interface with the robot. And you see that they have a set of different maneuvers to follow. The more complex the robot, the more maneuvers we need because we have more degrees of freedom to control. Now, the first step is identifying the most important motion features. So the most important body parts. So we run this feature selection, which is based on the variance of each body part in terms of Euler angles and the correlation with the robot actions. So you see that in this case, automatically, our algorithm can identify the torso as the most important body segment, even though the rest of the body is, as in a kinematic chain, is moving as well. Now, our algorithm is capable of recognizing the torso as the most important motion feature. What happens if a person moves in a different way, as we saw before? For instance, if a person wants to imitate the robot with their hand, we run the same algorithm and we see that the algorithm is capable of identifying, in this case, the right hand as the most important motion feature. So this person, in case, will be able to control the drone using the right hand. And then we validated our methods in a teleoperation task. So we translate human motion into robot action through this personalized mapping, and we asked them a set of subjects. In this case, there were 32 subjects to control the robot, to steer the robot through this path made out of waypoints. And we basically measure the error in teleoperation. So we try to quantify the effect of using personalized mapping. And what we also did is to test this in hardware. So in this case, you have the same exact protocol, but instead of flying in simulation through waypoints, we had the person controlling the real drone. So we tested the interfaces both in simulation and hardware, and we showed that using a personalized interface, people can learn faster to control the robot. So if you look at the plot on the right of the screen, we compared our personalized mappings, both linear and nonlinear in blue and green. You see there are not much difference between the two, with a remote controller and a non-personalized interface. And in this case, the non-personalized interface was actually the flight jacket. So a fixed gain between torso motion and robot commands. And what you can see is that if people use a remote or a non-personalized interface, they need some time, in this case, 30 to 30 waypoints, which corresponds pretty much to a minute, 2 minutes, to get confident and reach this performance plateau, so this low error at the end. Whereas if they use a personalized interface, they're able to control the drone with very little error from the beginning. So this is our first result. And this is the first study we run. Now, the second study goes towards generation of body-machine interfaces to control different robots, because this method was tailored to the control of a fixed wing, which is a simple robot, if you want, with a few degrees of freedom. The problem when you want to control more complex robots, and in this specific case, we considered a fixed wing drone with controllable speed, which has 3 degrees of freedom, a quadrotor drone, which has 4 degrees of freedom, and a robotic manipulator, which is a completely different robot with 6 degrees of freedom. You can move on the 3 axis and rotate on the 3 axis, so you have 6 degrees of freedom. And the problem with this is that people show more complex behavior, so they move more body parts at the same time, and also more heterogeneous behavior, meaning that from one person to the other, you see a lot more differences in how they move compared to what we've seen before for the fixed wing. So this is an example of the motion identification protocol for this kind of robot. So the fixed wing with a controllable speed. It is exactly the same experiment that we saw before. Instead of having the track in red of the robot, we show arrows. So it's easier to see what the drone is doing. And you see that this person, for instance, this is one example of the 30 subjects we had for this experiment. They're doing exactly the same thing. So they're moving the torso. This is a very common spontaneous interaction strategy for controlling drones. And then when you have the speed varying maneuvers, which are coming in a second, this person is moving mostly their arms. So this is the speed up command for the drone, and this is the slow down command for the drone. So you see that you have many more degrees of freedom of the human body which are involved in the control of this robot. So in this case, just identifying a set of motion features is not sufficient, because arms motion, we don't want to translate it into roll and pitch commands. So what we did is to leverage what is called in human motion studies the concept of synergies. So synergies are functional motor units require the coordinated action of several body segments. For instance, this moving the arms to the front or grasping is one motion synergy, because you control different degrees of freedom of your hands in a functional way, as if it was just one single action instead of moving 27 degrees of freedom. And we identify the synergies through dimensionality reduction, and we do it with PCA. So what we did, and I show you the visualization of this in a second, we first compress all the motion of the person in one synergy per degree of freedom of the robot. So for the roll commands, you have one synergy. For the pitch command, you have another synergy. And for the speed, you have the third. And we just take the first principal component of these synergies. And then what we did, we have two variants of our method. The second one just takes into account the motion variables that are mostly used for each synergy. So we cut everything else that is, if you want, secondary in the motion. So this is how it looks like. This is the motion of the same person. So you see that for the roll maneuvers, the two avatars on the right, which correspond to the roll actions for the drone, they're actually moving, whereas the others are basically standing still, because the compression just takes into account certain degrees of freedom. For the pitch maneuver, you see just the orange guys moving, and that is because they are the torso pitch. This kind of motion is related to that motion synergy. And you won't see a big difference from the front to the back, because here it is quite clear what the person is doing. Whereas for arms motion, you can see there is a big difference between the front and the rear avatars, because the rear avatar is not moving the torso at all, because that is a, if you want, minor action in this kind of synergy. So first we identify the synergies, and then we run regression on the synergy instead of running them directly on the human motion features. So this is how the performance evaluation looked like. So this is the control of the fixed wing drone. We ask the person to go through waypoints. In this case, they're visualized in a different way, but it's exactly the same task. And this person is moving in a completely different way. We had a lot of subjects, so you see a lot of variability in their motion. This on the right is the control of the quad rotor, which is very similar. We asked the people to go through waypoints as well. And for the manipulator, instead, we have a peg and hole task, where the person had to insert this little blue peg into the hole that you see in the simulator. And this is done, in this case, by the motion of the right hand. So each person had a different mapping. Each person had a different interface. And we realized that by validating this both in simulation and hardware, people still can learn faster how to control the robot compared to remote controllers. So in this case, you have in blue the joystick and in red the proposed interface. And you can see that in the first run of the experiment, everybody had to go through 2 runs. The motion-based interface show higher performance and better results. Also, we evaluated the user feedback, so how they liked and how they felt in terms of cognitive workload during the operation. And we show that motion-based interfaces can reduce the cognitive workload. This is a standard questionnaire for a cognitive workload. It's called the NASA TLX. And here we demonstrate that people felt less mentally challenged, mentally stressed during the deliberation, meaning that they didn't have to think about what to do to control the robot because it was a natural motion. They also preferred consistently the motion-based interface. And finally, we show that using this feature selection, so cutting the principal components of the interface, can be a crucial step to make the interfaces usable. As a third topic, we speak about online adaptation of body-machine interfaces. So the problem here is that interfaces are normally fixed and they don't adapt to a person's preferences. But the person might want to switch from, a torso kind of motion paradigm into a hand motion paradigm to control the same robot if they are tired or injured, or if they want to switch between strategies depending on the task. For instance, you have a complex task that requires you to move a lot and very fast. You want to do it with your hand because you have, it is more dexterous. But if you want to fly over the lake, there's no need to have all of this dexterity. You might want to use the torso because it's more relaxing and less tiring. So how to do this? We run, again, a similar user study, but we asked people to be a bit more creative. So we had 4 runs for each person on 12 subjects, and we asked them to switch interaction strategy every time. And we realized that the most common interaction strategies are actually the torso that we've always seen, interacting using the right or the left hand, and steering wheel kind of action, like if they were driving a car. This is what most of the subjects displayed during this imitation task. So first we identify the control strategies, then we run a clustering algorithm and a classification algorithm that is capable of identifying online during the operation which body part or which strategy the person wants to use. Then we generated the mapping using the same method as I shown before. We implemented the HRIs and we tested them in a similar way in the previous studies that I've been showing. So this is how it looks like. First, here you have a person controlling the drone using their torso motion. I think the video is stuck. I'm sorry. So here we first ask them to move the torso to control the flight of the drone. And at a certain moment in time, you'll see the avatar switch to the right hand. This person moves the right hand. The algorithm realizes that now we are switching to right hand control interaction. And now the person can control the robot using directly the right hand without, moving switches or pressing buttons, just showing how they want to do it. First, we run this first experiment on 20 subjects, and we show that people can learn how to use different strategies simultaneously. So switching between one and the other, they can still control the drone efficiently, and they can remain on the correct strategy that is shown by the avatar for 95% for the steering wheel, for instance, to 98%. Anyways, more than 80% of the time of the first of a certain when a certain strategy is shown. And also they can switch from one strategy to the other. They can learn how to do it. So in the first run of the experiment, they took in average more than 6 seconds to switch from one strategy to the next. During the second run, they took less than 3 seconds. So people can actually learn how to switch between strategies efficiently. And then we run a second study with a path with different difficulty levels. So you have here in green, you can see the easy maneuvers. Then you have a white segment where people are asked to switch. And then you have more complex maneuvers. And we ask each subject, so we had 10 subjects, we asked them to pick their preferred interaction strategy for the easy maneuvers and their preferred interaction strategy for the hard maneuvers. And it turns out that most of the people prefer to use the torso for the easy maneuvers and their dominant hand for the hard maneuvers, for the reasons that I basically told you at the beginning of this part, of the experimental part. So we had 10 more subjects using the torso, just the torso, without being able to switch, and 10 more subjects using just one hand without being able to switch, to evaluate how efficient and how effective it is to actually have the option to switch control strategy during teleoperation. It turns out that, and you can look mostly at the hard maneuvers, are the most interesting ones. So in the second row of this table, you can see that for the hard maneuvers, being able to switch can improve performance up to 60%, so can reduce error by 60% in the case of the torso and 27% in the case of the hands, just by the fact that they are allowed to switch or not. So if you're allowed to switch, you can reduce your error by up to 60% with respect to a fixed interface. And also we realized that in terms of user feedback, people felt less mentally demanded and less physically demanded when being able to switch between interfaces. So people using just the torso felt 72% more tired than people able to switch, and felt 23% more mentally demanded than people who were able to switch. And it was the same for both torso and one-hand groups. So we improved the user experience by allowing people to switch control interfaces with respect to standard fixed interfaces. So this concludes my presentation. I will just summarize briefly the main results. So first, we show that personalized body-machine interfaces can help people learn faster. In the second study, we show that leveraging knowledge about human motion, such as its synergistic nature, can help creating more general and effective interfaces. In the third study, we show that allowing users to switch between motion strategies during interoperation can increase performance and improve the user experience. And finally, these methods can be in principle applied to different platforms and systems, and like more robots, or for instance, prosthetic limbs. This concludes my presentation. Thank you for the attention.